So the topic for this video is the Lagrange interpolation formula. So the idea here is to find a polynomial of least degree that is a single variable polynomial that goes through a certain number of points. So I'll build this formula by going through progressively more complex examples. So we'll start off with the most simple example. So this is the example where we only have one point that we want our polynomial to go through. So we'll call this point x1, y1. And to build a polynomial that will go through that, we can actually find a degree 0 polynomial that will go through that. We can just use the polynomial y is equal to y1. And we'll find that this is a general rule that the degree of the polynomial that you need in order to make it go through a certain number of points is actually that number of points. We'll call that little n take away 1. So in this case we've got 1 point and the degree polynomial is going to be 0. When we have 2 points, the degree of the polynomial needed is going to be 1. When we have 3 points, we'll find that the degree of the polynomial is going to be 2. So here I've drawn on that degree 0 polynomial, y is equal to y1, and you can see that that is a perfect example of a polynomial that's going to go through this single point here. Next, now let's go to the slightly more complex example. So we'll have 2 points now. So we've still got our original point x1, y1, and now we've got a second point which is x2, y2, and we want to build a polynomial of least degree that will go through those 2 points. So it's now going to be necessary to have a degree 1 polynomial. Hopefully you understand that you're not going to be able to make a degree 0 polynomial that's going to go through those 2 points because there's no horizontal line that goes through both of them, unless of course both of the points just happen to be on the same horizontal line, which isn't the general case. So we're trying to build a formula that will work for the general case, but it's true that if you had the 2 points on a single horizontal line that you would then be able to find a degree 0 polynomial that goes through both of them. But for the general case, we're going to assume that the 2 points aren't on the same horizontal line, and we now want to build a degree 1 polynomial that's going to go through both of them. And the Lagrange interpolation formula for this is given here, and I want to explain how you get to this. So let's examine this bit first. So the function is going to be y is equal to, and then the variable is x. Remember, all these other things that you've got here, these are specific numbers. So the y1, the x2, the x1, the x2, all of these are specific numbers given in your problem. So they're not variables. So we just have here a degree 1 polynomial in this variable x. So where does all of this complex stuff come from? So the easiest way to understand this is probably to think about what's going to happen to this function when you evaluate it at x1 and then evaluate it at x2. So let's think about evaluating it at this point here. So we want the answer to equal y1 when you stick x1 into here. And if you look at this, if you look at this second bit, when you put x1 in here, you get x1 minus x1, so you get 0. So that bit totally goes to 0, and that's exactly what we want to happen because this is the bit with y2 in it. We don't want this function to equal y2 when you put x1 in. We want it to equal y1, so it's good that that bit goes to 0. Then when we look at this bit over here, if we put x1 in here, we get x1 minus x2, and then we're dividing by that same constant, x1 minus x2, so that this just turns to 1, and then you get 1 times y1. So it gives exactly the right answer when you evaluate it at x1. So this is going to go through this point, x1, y1. Then when you consider what happens when you evaluate it at x2, well, this is why we needed this x minus x2 here, so that the exact same thing that happened for x1 over here happens for x2 on this side. So when you put x2 in here, that's going to go to 0, so this bit totally vanishes, and that's good because you don't want y to equal y1 when you plug in x2 into this. And then when you put in x2 in here, you'd get x2 minus x1, and then underneath you've got x2 minus x1, so those will cancel to make 1, and that'll give y2, so it's then correct for this point here, and that's why these bits are underneath here. If you imagine taking those away, making a simpler formula, the reason that we've got the x minus x2 and the x minus x1 in there is so that those vanish to 0 when we're talking about the other point that we're not interested in. So in this case, the x2 point is the one we don't want it to, we don't want y1 to be the correct answer there, so we need to have a 0, this to go to 0 when you put in x2. So that's the reason we've got that. And likewise on this side, in front of this y2, we don't want x1 to give y2 when you plug it in here, so we want a 0 there. But we then want it to be correct when you put in the right one, so when you put in x2 here, we want this to be correct, and that's why you have to scale it by this, so that it's going to be correct at its point. So what you overall have here is a brilliant formula that goes through both of these points, and you can understand exactly why it does that. And it's a linear formula, it's a degree 1 polynomial, so it's going to be a straight line through those points. So we can do some algebraic manipulation to rewrite this, so we can get it over the same denominator by multiplying one of them through top and bottom by -1. Now, it's customary to get it over the denominator x2 minus x1, so we'll multiply this one, top and bottom, by -1, and we can then combine the two numerators together, and we end up with this. So this bit is from here, and then this is just the negative of this, all now over x2 minus x1, and this is a famous formula. This is called the linear interpolation formula. Now, we're going to generalize this concept that we've used here to harder problems where we've now got 3 points, and we're going to be able to build a degree 2 polynomial that's then going to go through those 3 points, and so on. We can continue it on, and this is what's called the Lagrangian interpolation formula, and the process is called Lagrangian interpolation. So now the next case up, and as you can see just from looking at the answer that I've written down here, it gets more and more complicated the more points you add in. So let's do this though. So we've now got 3 points, so we've added in the third point, x3, y3, and we now want to produce a polynomial that is going to go through all 3 of those. And you can see that there is no degree 0 polynomial and there is no degree 1 polynomial that is going to go through the general case of 3 points. Of course, again, you could have it be the case that you have all 3 points on a single horizontal line, in which case there is a degree 0 polynomial that goes through all 3. But in the general case, you're not going to be able to find a degree 0 or a degree 1 polynomial. So you're now going to need a degree 2 polynomial, and this is going to be the formula for that degree 2 polynomial. So the logic behind it is exactly the same as the logic behind this one. And again, the reason that this is going to go through all of these 3 points is best seen by just plugging in the values. So again, let's think about what this evaluated at x1, y1 is going to be equal to. So again, we've got 3 terms, and these 3 terms, 3 parts if you like, are each of the 3 y values. So we've got y1, y2 and y3. So we want, when we plug in x1 into this, that the answer is y1. We want for x2 the answer to be y2, and we want the answer for x3 to be equal to y3. And you can see why it's going to be that from looking at these. So when you put in x1 here, x1 minus x2, x1 minus x3, and we've got those 2 numbers in the denominator here, so those will cancel to just make 1, so it'll give you y1. When you put in x1 to these 2 parts, both of these have got x minus x1 here, so you're going to get 0. So both of these parts are going to go to 0, and that's the reason the x minus x1 has to be in both of these, and it's not in here. Instead, you've got x minus x2 and x minus x3, so that x2 and x3 will make this bit vanish. They have to be there so that these other parts will vanish when you put in your point x1, so that you just get this one giving you an answer. Next, so it's correct for this first point. Next, let's put in the second one, so x2, and it works exactly the same way. So here we've got an x minus x2, here we've got an x minus x2, so these 2 are both going to go. This is the only one without the x minus x2, so you put in x2 into both of these, and then that's the reason this bit at the bottom has to be there, so that you don't get some number times y2, you just get 1 times y2, so you have to divide through by whatever x2 minus x1 and x2 minus x3 is equal to, so this all turns to 1 times y2. so it's going to be correct for that point. And then finally this point, so you've got the x minus x3 in both of these ones, so those two are going to go, and then this is the only one where you don't have an x minus x3, so you put in x3 into there, and that's the reason these have to be there, so that those cancel to give 1, and then you just get y3. So you can see that this thing is a degree 2 polynomial, so if you were to multiply all of this out, remember these are just numbers, these things on the bottom, there's no x there, these are just specific numbers, so it's not some sort of rational function with powers of x in the denominator here. No, it is just a quadratic in x. The highest degree terms you're going to have are x squared, so it's going to be a degree 2 polynomial in x, and it is correctly going to go through all of these 3 points. So we could go on with specific examples, so we could do 4 points and get a degree 3 polynomial, we could do 5 points and get a degree 4 polynomial. Instead, what we're going to now do is do it for the general case, so we're going to do it for n points and get the general Lagrange interpolation formula. So it's going to give you a polynomial of degree n minus 1 that will, I guarantee it, go through your n points. So we're going to say we have these points here, x1, y1, x2, y2, all the way up to xn, yn, and we now want to build a formula for this n minus 1 degree polynomial that's going to go through all of these points. So let me explain this. So we have our function in x, y, is going to be equal to the sum from I is equal to 1 to n of all of the y values of the points, yi, times this structure here. Now, each of the yi's is equivalent to these. Each of these terms is going to be one of the terms in the sum, one of the y terms. So here we have the sum from I is equal to 1 to 3 of yi, and you have each one of the yi's therefore added together. So you have y1 plus y2 plus y3. So that's where that bit comes from. And then this structure that each one of the yi's is multiplied by is the equivalence of these bits here. So let's have a look at this. So this is the product from j is equal to 1 to n, but you exclude j is equal to I, and you're going to product together x minus xj over xi minus xj. So I think to make sure that you understand this, it's best to do a concrete example. So we'll take the concrete example of n is equal to 3 and make sure that when we put in n is equal to 3 here, we get the same thing that we had earlier. So here we go. So n is equal to 3. So this now becomes equal to this. The sum from I is equal to 1 to 3 of yi, each yi times the product from j is equal to 1 to 3, where you exclude j is equal to I of x minus xj over xi minus xj. So let's work this out now. Let's write a bit of this out. So let's get rid of this summation sign and actually write out the full sum. So we have y1 plus y2 plus y3, so all the i's, and now for each of them they need to be multiplied by one of these products. So for y1 the product is going to be from j is equal to 1 to 3, where you exclude j is equal to 1 because that's the I value for this term, and then we've got x minus xj over, and now we've substituted in for I 1 here, so x1 minus xj, and we'll think about what this product is going to be in just a moment. The next one we've got y2 times the product from j is equal to 1 to 3, where you exclude j is equal to 2, times of x minus xj over x2, substituted in for xi now, minus xj. And then finally, exactly the same for this third term, you've got y3 times the product from j is equal to 1 to 3, where you exclude j is equal to 3 of x minus xj over x3 minus xj. Now thinking about what each of these products is equal to, so let's just do this. So plug in the numbers. So we're going to have j is equal to not 1, we're excluding 1. So we'll have j is equal to 2, and then we'll have j is equal to 3, and we want to multiply the two by one another. So we're going to have x minus x2 over x1 minus x2 times x minus x3 over x1 minus x3. And that's exactly what you get here. So this bit, x minus x2 over x1 minus x2, that's from j is equal to 2. And this bit here, x minus x3 over x1 minus x3, that is from j is equal to 3, so that gives that correct coefficient for y1. Then it's the same for y2, so we're now going to exclude the number 2, and the reason that you're excluding that is because you don't want the term x minus x2 in front of here, because that's the term that makes it vanish and go to 0, but you don't want it to equal 0 at y2, for y2, because y2 is the value at the point x2. You want it to equal 1 there, and remember that's the reason all these denominators are here, so that when you plug in x2 here, it's going to equal 1. So doing this then, so we're going to get x minus x1 over x2 minus x1, that's that bit there, multiplied by x minus x3 over x2 minus x3, which is j is equal to 3. And then, as I say, you haven't got the term for j is equal to 2 because you're excluding that. And then finally, this third term, you've got j is equal to 1 to 3, but you're excluding j is equal to 3 now, again, because you don't want that term x minus x3 over x3 minus x3. That's a nonsense term. You definitely don't want that division by 0. So that's the reason you're excluding the j is equal to 3. So you're going to get x minus x1 over x3 minus x1, which is that bit there, and then x minus x2 over x3 minus x2, which is that bit there, which is j is equal to 2. So there's that concrete example, and you can see how this formula works and gives us this for n is equal to 3. So I hope what you can appreciate then is that this thing here, this is just the polynomial in x that is equal to 1 when you put in xi, the right x value that you want to be paired with your y value, and it's equal to 0 when you put in all the other x values. And that's why this is going to work. It's going to give you the correct y value for each of those x values, because it's going to be 0 at all the other y values in this summation, and it's going to equal 1 at the correct y value. And that's going to be true for all of these points here. Just one final effort to make it crystal clear. So I've taken this and I've written out the summation from I is equal to 1 to n, so that we've got the n terms here. So we've got y1 times its polynomial, plus we would have y2 times its polynomial, plus y3 times its polynomial, all the way up to yn times its polynomial. And each one of these things that you've got in front of these y's, it is the correct thing that is going to vanish to 0 for all the other x values. So for y1 term, it's going to be 0 when you put in x2, x3, x4, x5, all the way up to xn. Because of these terms up here, you've got the x minus the xj's from j is equal to 1 to n, but you're excluding that first term, the j is equal to 1, because that's where you actually want it to equal 1. And the thing that's making it equal 1 is that you're then dividing through by x1 minus all these xj's, so that when you put in x1 into this polynomial, it will give you 1. Meanwhile, on all the other ones, you won't have excluded j is equal to 1, so you will have an x minus x1 term. So when you put x1 into all of those, they will vanish, so that you just get that the answer is y1. So that's working for every single one of these respectively. So just to take this one here, for yn, if you put in xn into here, it'll give you 1, and if you put xn into all the others, it'll give you 0, so that then the answer is just yn. So it's working exactly that same way for all of these points, so that it gives you the perfectly right answer for all of those points. So a few final important points to say just before we end the video. So this polynomial that we found of degree n-1 that goes through all our n points, this is the only polynomial of degree n-1 that goes through all those points. You can't find another polynomial that will go through all of them. And the reason for that is if you imagine the opposite, so imagine that there were two different polynomials that go through all of these n points, and they're both of degree n-1. So we could imagine that f of x is our Lagrangian interpolation polynomial, and we have another one, g of x, that is different to it, so the coefficients are not all the same. Then consider what would happen if we subtracted these two polynomials from one another. So we took our f of x and we subtracted off g of x. The thing that we would get is still going to be a polynomial, and it's going to have degree at most n minus 1. And whether it's less than n minus 1 will depend on whether the coefficients of the first highest term were the same. If they were the same, then they were vanished, and now this will have degree less than n minus 1. But at the maximum degree it can possibly have, however, is n minus 1. It can't suddenly have got a higher degree. When both of these two polynomials were degree n minus 1, when you subtract them, you can't suddenly end up with a degree n polynomial. Basic algebra. Now here's the problem with this. Because these two polynomials both went through all of these points, that means that now if you consider the two of them subtracted at all of these points, so if you put in x1, x2, x3, all the way up to xn into this, you're going to get 0. Because if you put in x1 here, f of x1 and g of x1 were going to equal the same thing, so you're subtracting it from itself, so you'll get 0, and so on for all the others, because of the fact that they went through all of these points. That means that this new polynomial, f of x minus g of x, that has degree at most n minus 1, is 0 at all of these points, so has n roots, therefore. These are all going to be roots of this polynomial, x1, x2, x3, all the way up to xn. They're all going to be places where the polynomial turns to 0. So they're all going to be roots of this polynomial, but that's a problem because we know that a polynomial can have maximum in the real line, its degree, number of roots, but its degree is only n minus 1, so it can have a maximum of n minus 1 roots. But here we're saying it's going to have n roots. The only way for that to work is if it is actually just equal to 0 everywhere. So this has to equal 0, and then suddenly it can have all of these points as roots, because it's 0 everywhere, so it is going to be 0 at all of these n points. That's the only way to reconcile this. So therefore f of x minus g of x has to equal 0, and therefore f of x has to equal g of x. So you can't find another degree n minus 1 polynomial that goes through all of these points. You could find a polynomial of higher degree, so maybe 2n or 3n. You could find a polynomial of higher degree that would still go through all of these points, but not another polynomial of degree n minus 1. So this is the only polynomial of that tiny minimal degree that will go through all of these endpoints. The final thing I want to say before we end this video is just a warning. So let's say we had these 6 points here, and we wanted to find a Lagrangian polynomial that would go through all of these 6 points. Now you might think this is wonderful, I can build curves that will go through whatever points I want. You can, but it might not be quite as you expect it to be. If you think that the Lagrangian polynomial is going to be something beautiful, give you a beautifully fitting curve that's going to go through all of these points, you're going to be very disappointed. It's not. Instead, the thing you're going to get is going to look more like what I'm about to draw. So here we are, I've drawn it on. So the point is that it wiggles around, it goes up, it goes down, it like this. You won't get a beautifully fitting curve from this. Its curve fitting ability is not very good. It will go through all of the points, but in between them it will be going up and down and not plotting a beautifully smooth curve in between the points the way our intuition would like. So that final point is just a warning. Be careful about using this to predict values between your points. It might be the case that you get very bad answers if you try and predict the value that you think should be in between two of your data points that you're using to make this polynomial. So overall, Lagrangian interpolation gives a beautifully simple answer to the question of if I start off with n points and I want to build a polynomial that will go through all of those n points, what is the smallest degree polynomial that I can build that will do that? And we've seen how the answer is 1, beautifully simple, and 2 is unique. So there's only one polynomial of that smallest degree that will go through your n points. The final thing we saw was just a warning about how the curve that you end up with might not be quite what you were hoping for when you were thinking, I'd like to build a curve that will go through all of my endpoints. Instead, it might be rather waggly, like so. Remember, it is a polynomial, and polynomials, especially when you get higher and higher degree, tend to be quite waggly, especially when they're complex. So thank you for watching. I hope you found that understandable and helpful.